All right, welcome back, College Math. Let's look at a first example. We're going to rewrite the following exponentials as logarithms, or vice versa. So we're going to either rewrite an exponential as a logarithm, or we're going to rewrite a logarithm as an exponential. And then just kind of as an aside, confirm that they're true. Okay, so all of what you're going to see here are facts. There's nothing to calculate. There's nothing to find. All we're going to do right here is kind of practice rewriting stuff as each other, kind of being fluid in that. That way we can get a better understanding of, what is this logarithm thing, right? So 3 to the 4th equal to 81. Like if we plug that into our calculator, then we get that's true, right? So let's just rewrite it as a logarithm. Okay, so let's do yellow. So log base, the bases are going to be the same. So if the base of the exponential is going to be the base of the logarithm, so log base 3. And I'm switching the inputs and the outputs. My answer is 81. So that's going to be the input of my logarithm. Log base 3 of 81 is equal to 4. Okay, that's how we rewrite this. Okay, and let's just confirm, right? The little question we ask ourselves that I put up here. Okay, 3 to what power gives me 9? 3 to what power gives me 9? That's pretty much what I'm asking myself, or that's what I'm saying here. 3 to what power gives us 81? Oops, sorry. 3 to what power gives us 81? It's 4. 3 to the 4th power is 81, and we know that from here. Okay, so this is the rewritten version of this fact. This is also a fact, right? Something like if you're kind of a more visual type of person, notice kind of what's going on, how to rewrite. So 3 is my base. Inside my logarithm is the 81, and it's equal to 4, using kind of this little circle trick. If you're kind of like wondering, like, if you're not really seeing kind of where I'm putting all the numbers, right? So let's see it in part B. 7 to the 3rd is 343. That's true. So log base 7, right? If I do that circle thing again, 7 is my base. 343 goes inside my log. My answer is 3. So log base 7 of 343 is equal to 3, because 7 to the 3rd power is equal to 343. And it's kind of the same. You can do that same little circle visualization with the log. 7 to the 3rd power is equal to 343. So rewrite it back into the exponential. 3 to the 4th power is equal to 81. All right, let's do a few more. 16 to the 1/2 power is 4. We know that's true, right? The 1/2 power, that's our square root. Square root of 16 is 4. All right, so let's rewrite that as a log. Log base 16. Okay, start with the 16 as your base. 4 is the input. 1/2 is our answer. Log, ooh, I went against what I just said. Log base 16 of 4 is equal to 1/2. All right, one last one. 27 to the 1/3 power is 3. That's true because the cube root of 27 is in fact equal to 3. 3 times itself, or sorry, what times itself 3 times is 27. That is for sure 3. Okay, so log base 27 of 3 is equal to 1/3. Okay, and so notice kind of what's going on. The base in these cases over here in the top, the base was smaller than our input, so the exponents were like whole numbers were bigger than 1, right? But now in these two cases down here, the bases were bigger than the inputs. So whenever that happens, when your base is bigger than the input, then you're going to get a fractional value, but it's also going to be less than 1, right? Because we could also get fractions for these right here potentially, but they would be fractions bigger than 1, like say 3/2, 7/4, 12 over 5, etc., right? So just kind of a nice little observation to make. Okay, let's keep going. Now we're going to flip it. We're going to start with a log and rewrite these as exponentials. Okay, so let's just kind of see what's going on here. So first, notice the first one. Log of 100 is 2. Okay, that's a fact, but the issue is that we don't really know what the base is. Doesn't give us a base. Okay, so here's kind of a nice little thing to remember, because this is just kind of the standard that, you know, someone developed a long time ago. Who knows who it was? Whenever you don't see a base, the base is 10. Okay, so maybe write this down really quick. When there is no base shown, right, then the base is 10. And then I guess actually maybe a little more specific, because we're talking about logs here. When there is no base in the log, the base is 10. So whenever you just see log of x is equal to something, then this base is 10. All right. They call this the common logarithm. Okay, so then now that we know it's 10, I don't know why I erased the 10. Let's just leave it there. Well, now that we know that the base is 10, okay, let's rewrite. We can use that little circle trick, right? 10 is our base, so it's going to be the base of the exponential. 10 to the power of 2 is equal to 100. 10 to the power of 2 is equal to 100. And that's true, right? 10 squared is 100, right? So you kind of see, hopefully now you're kind of seeing what's going on, right? Let's do the next one. 4 to the power of negative 2 is equal to 1/16. 4 to the power of negative 2 is equal to 1/16. Ooh, sorry. I meant that as a fraction bar, and then I write it. I kept going as negative 1/16, right? And that's true, because remember, the negative exponent, what we can do with that, 4 to the negative 2, that's the same thing as 1 over 4, make it positive, squared. And we know 4 squared is 16. Okay, so that's true. All right. So just kind of remember that little circle visualization if you're having trouble with this stuff, right? So now next one, 1/2. So log base 1/2 of 16 is equal to negative 4. 1/2 to the negative 4 is equal to 16. So 1/2 to the negative 4 is equal to 16. All right. So now you can think of this negative, like when we deal with negative exponents, you can think about just flipping, right? So we would do the same thing here. All right. So I'm flipping whatever I see on the inside. So 1/2 to the negative 4 is equal to 2 to the positive 4. And that's equal to 16 for sure. All right, so that's kind of what our negative exponents do. One last one. 81 to the 1/2 power is equal to 9. Is that true? 81 to the 1/2. Well, 81 to the 1/2, remember that's the square root of 81. And yes, we know the square root of 81 is 9. Okay. All right, so that was just kind of a little bit of practice with rewriting logs as exponentials, rewriting exponentials as logs. Now let's actually go ahead and calculate some of these logs, okay? So find the value of the following logarithms by rewriting as an exponential first. All right, let's start with the first one. Log of 1,000, we don't see a base, so we know it's base 10, all right? So we're trying to find the answer to this, right? Well, write equals question mark, because that's our mystery. That's the mystery we're trying to solve, okay? Well, then now we have something on the other side of the equal sign, so let's rewrite as an exponential. 10 to the mystery power is equal to 1,000. 10 to what power is equal to 1,000? That's the question we asked ourselves above with the log base 3 of 9. 3 to what power gives me 9? That was 2. 10 to what power is 1,000? Well, that question mark is 3. So the answer to this logarithm, the answer to log 1,000 is 3, because 10 to the third power is 1,000. Okay, that's our answer. Let's do some more. Log base 2 of square root of 2. So don't let that freak you out. Just let's keep going. This is equal to a mystery. So then rewrite as an exponential. 2 to what power is equal to square root of 2? 2 to what power is equal to square root of 2? Well, how do I rewrite the square root as an exponent? That's 2 to the 1/2. Oh, well, 2 to what power is equal to 2 to 1/2? That's directly the same, right? So my mystery is 1/2. So then log base 2 of square root of 2 is equal to 1/2, because 2 to the 1/2 power is the square root of 2, and we know the square root of 2 is, 2 to the 1/2 power. All right. Log base 4 of 1024. Okay, equals to mystery. 4 to what power is equal to 1024? So 4 to what power is equal to 1024? Okay, you might need your calculator for this in case you don't really know that off the top of your head, right? We're going to need to pray that it's going to be a nice even number and not some fraction that we don't know. Well, we know 4 to the 3rd power is 64. Let's use our calculators. 4 to the 4th power, that's 256. 4 to the 5th power, 1024. So we know this mystery is 5. So log base 4 of 1024. Sorry, that's not a negative. I just accidentally, that was a miss, right? Log base 4 of 1024 is equal to 5, because 4 to the 5th power is equal to 1024. Okay, we're on a roll. Let's keep going. Log base 6 of 1, what is that equal to? So 6 to what power is equal to 1? All right. Well, what to, anything to what power is 1? We know that's 0, because every time we raise something to the 0th power, we get 1. So log base 6 of 1 is equal to 0. And this is actually going to be true. This is like a little fact. This is a logarithm property, that log of any base a, okay, as long as it follows those rules above, that a is positive and it's not 0 or 1, log base a of 1 is always, always, always going to be equal to 0. Sorry, I ran out of room. Let me rewrite that in one line, and I'll do it in a different color. So log base a of 1 is always going to be 0. This is a true fact that works all the time. Okay, it's a property of logarithms. Okay, 2 more examples and then we'll kind of wrap things up, okay? So log base 17 of 17. Okay, what are we asking ourselves? Mystery. 17 to what power is 17? 17 to what power is 17? Well, I'm going to get the same thing as my original base. What does this exponent have to be? 1. 17 to the first power is equal to 17. So the answer to this is 1. Log base 17 of 17 is equal to 1. And that's another property. Log, let me do it in a different color for our property. Log base A, remember, same thing. It's got to be positive and then not 0 or 1. Log base A of itself is equal to 1. That's another logarithm property. We'll talk about all the logarithm properties in the second part of this section of, we'll do it in D.2. Okay, and that'll be the next video you watch. Okay. Last one. So log base 6 of negative 36, mystery. So 6 to what power is equal to negative 36? So 6 to what power is equal to negative 36? Okay. Well, maybe what you're thinking is, okay, well, I want 36. I know 6 to the second power gives me 36. But will 6 to the second power ever give me negative 36? Well, what if I did 6 to the negative 2? No, that doesn't have anything to do with the sign. That'll just make it be 1 over 6 squared, which is 36. 1 over 36. Okay, so that's not good and that's not good. Okay, let's think back to something we talked about for our exponential function. So exponential, oops, sorry, thought I had my pen open. So for an exponential function, what was our domain and range? Our domain was all real numbers, so all the reals. And then what was our range? It was all positive numbers, right? Our range was y bigger than or equal to 0. Sorry, bigger than 0, not or equal to. So that means the output of our exponential, the answer to an exponential expression, should always be positive. It can never be negative. Okay, so this is impossible, right? Because I will never get a negative output from an exponential, which means this is impossible. Okay. So that kind of tells us something that I actually just realized we didn't talk about above, right? But it's good that we developed it this way. The domain of a logarithm, so for a log, right, the domain is now kind of this, right? But instead of y is greater than 0, it's x is greater than 0, okay? So I can only plug in positive numbers into a log, okay, because of the fact that the domain of a log is x is bigger than 0. Okay, and then the range is actually all reals. Okay, and remember, that's kind of the definition of an inverse function, right? The log is the inverse of the exponential. So the inputs and the outputs switch. Well, that means the domain and the range switches, right? If my domain is all reals on the exponential, then now the range is all reals on the logarithm. If my range was only positive numbers for my exponential, now my domain is only positive numbers for my log. Okay, so moral of the story is that this is not real. So no real solution. If I can write correctly. No real. What is going on with me? No real solution. No real solution. Write down no real solution, you guys. I'm sorry. My hand is refusing to write correctly for some reason. There we go. No real solution, right? If you research this a little bit, you'll actually find that this has a complex solution, and not complex as in complicated, but complex as in, involving imaginary numbers, but we're not going to get into that. But if you're curious, maybe Google research, what happens when I take the logarithm of a negative number. You'll find some interesting stuff. Okay. So important stuff about logs. Okay, just to kind of recap, what did we talk about? So log is the inverse of the exponential. Okay. And some of those properties we found, right? Log base A of 1 is equal to 0. Log base A of A is 1, right? And remember, for both of these, A is positive, and A cannot be 0 or 1. Nope, not 11. 1. And then the last thing we just found out, can't plug negatives into log. Okay, we can only take the log of a positive number. We can get a negative as a result. I can have a negative answer to a log, but I can't plug a negative into a log itself. Okay. Hopefully this kind of rings a bell. Hopefully you did learn about this in Algebra 2. And I really do strongly recommend to you that if you didn't, if for some reason, maybe you transferred in from a different school that definitely didn't get to this, or maybe in your Algebra 2 class, you just never covered exponentials and logs, it's kind of up to you to come seek help from me to understand this a little more, or maybe kind of do some research on your own time, look at some Khan Academy videos about exponentials and logs to understand this a little more. But please, please, please come get help from me if you're having trouble with this, okay? I will see you in the next one, you guys. Have a great rest of your day.